Question 19. A boat Q is moving with a speed of 18 kilometers per hour on a bearing of 270 degrees. To the captain Q, another boat P appears to be moving at 20 kilometers per hour on a bearing of 015 degrees. A. Determine 1. The actual speed of P. 2. The direction in which P is moving. At 12 noon, Q is 12 kilometers from P on a bearing of 290 degrees. Both boats continue on their current paths and at the same speeds. B. Find the time at which they will pass closest to each other in their subsequent journeys. And that's for 9 marks.
Hello everyone, and I hope you enjoyed my last video of the cylinder on the 2 inclined planes. Here we have a wee vector question on our hands. Quite a challenging wee vector. It assumes you've done a lot of vector work before, and this is bringing it all together. Now, we have 2 boats at sea that are relatively close by, but another close by because Q can see boat P, and it gets at the question. And we're asked to find the actual speed of boat P, and we're also asked to find the direction it's heading in. Now, the actual speed of boat P and the direction it's heading in, if we know that information, then we know the velocity of boat P, and that's what the question is asking really. What is the velocity of boat P? Now, the actual velocity of boat P is a velocity that would be measured by someone on the seashore. So someone's on the seashore and they're at rest and they're looking at boat P. They measure its speed and they measure its direction. That's the actual velocity of boat P as measured by someone at rest. But what information we're given this information. We're given information from the point of view of a captain on boat Q that's moving at 18 kilometers due west. The velocity of boat P appears, and that's the key word here, it appears to be on a bearing of 015 with a speed of 20 kilometers per hour. That's how it appears to the captain on boat Q. That should tell you right away this is a relative speed we're speaking about. This is the velocity of P relative to Q. It's not the other way about. It's the velocity of P relative to Q. And if we now know that the velocity of P relative to Q is the velocity of P, take away the velocity of Q, that's our starting point. As soon as we appreciate that, we've got a starting point and we can proceed. And when it comes to working out the magnitude of the velocity and the direction, well, that's something we've been doing before for many years. And here is the starting point for this problem. It's very difficult to see how we can proceed with this question unless we have something like this drawn. As you can see, I have my compass axis and I have my XY axis superimposed on that. That's for reference, and that's our necessary starting point. Now we start putting our information on this diagram. There is boat Q travelling 18 kilometers per hour on a bearing of 270 degrees. This means it's travelling 18 kilometers per hour in the negative X direction. And it's necessary to do that in order to get our components in a way that we're familiar with manipulating. And we can see that the velocity of Q is equal to negative 18x. That means it's travelling 18 kilometers per hour in the negative X direction. And there's no components in the north-south direction or a negative and positive Y direction. And there we have our other information given. This is the velocity of P relative to Q. It's the velocity of the boat P as it appears to boat Q. And we can see that apparent velocity according to Q, or from the point of view of Q, is 015 and 20 kilometers per hour. This is how the velocity of boat P appears to boat Q. And component form, well, that's 20 sin 15x, in other words, 20 sin 15 kilometers per hour in the X direction, and 20 cos 15 kilometers per hour in the Y direction. Now, once we have that, we are then in the position to solve our problem. And there is the answer. You don't really need me to take you through that, but we can see the answer in the bottom. The velocity of boat P has a magnitude of 23.2 kilometers per hour on a bearing of 326.4 degrees. And that is our answer. And I'm expecting most of you to be able to follow that yourself without further explanation from me. And there's our answer. Look at this for a second. Q is travelling in the western direction at a far greater speed than P. Therefore, from the point of view of Q, P seems to be travelling in the eastern direction. Think about that for a second. A. At 12 noon, Q is 12 kilometres from P on a bearing of 290 degrees. Both boats continue on their current path and at the same speeds. A. Find the time at which they will pass closest to each other in their subsequent journeys. When do these two boats pass at their closest? Well, before we can answer that question, there's information that we need. We need to know at what time do they start. Well, that is to say here 12 noon. Well, that's just t equals 0 seconds. In fact, t equals 0 seconds. At t equals 0 seconds, we need to know the position of these two boats are relative to each other, and we're told that. We're told they're 12 kilometres apart, which is one thing, but we're also told that Q is on a bearing of 290, and that's all the information we need. And that's we need to draw a diagram, and that would be our initial t equals 0 situation, 12 noon. Then we need to draw in where they are a time t later. What their displacements will be a time t later. Now remember, velocity times time is equal to displacement. Now we know what the velocities will be. They'll be the same as they were in part A. So what we can do is we draw boat Q a wee bit along the western direction, and we draw boat P a wee bit along the direction it's heading in. Then we can put in a position vector from Q to P. Or from P to Q, I should say, the position of Q relative to P. This is what we'll do here. And it's the length of that vector is the distance we're looking for. And we can use Pythagoras for that. And that will be a function of time. Then what we need to do is, that will tell us the relative displacements as a function of time. But we need to know when that displacement is a minimum, what will the time be when that displacement is a minimum? And there's a way to do that you probably know about, and that's how you proceed with this. But one of the large problems with this is knowing how to set it up. But once it's set up, it's relatively straightforward after that, and this is how we proceed. And there's our starting point. We can see that our boat Q is on a bearing of 290. And it's about to travel in its original direction, and boat P is at the origin, and it's about to travel in its original direction. This is our starting diagram. We must have this drawn before we really proceed. Then we look at the boats a short time later, or even a long time later, but the boat's been displaced along their directions. And we need to know the distance between these two boats. And that will be a function of time, as you shall see. First of all, we have to do is we put in our position vectors, RQ and RP. Then we find the position of Q with respect to P. And there's that vector drawn there, the position of Q with respect to P. And that's equal to RQ take away RP. Then we find the components of these vectors and subtract them. So you'll have to study that diagram to make sure you know what's going on. Let me explain the components of boat Q. Well, negative 12 cos 20 kilometers in the x direction, that corresponds to its original displacement at time t equals 0 seconds. Negative 18 t kilometers in the negative x direction, well, that corresponds to its displacement after t hours. Remember, it's travelling at 18 kilometers per hour. At 12 sine 20 in the y direction, well, that's constant, but it's not travelling in the y direction. It's not travelling north or south. It's just travelling due west. So those are the x and the y components of both Q. And similarly, we explain the x and y components of both P, which started to remember at the origin. And this is our solution. It should be relatively straightforward now. Notice in line 7 we have our distance squared, and that is a parabola, and we wish to find the minimum point of that parabola, and that is just calculus, and I'm assuming you know how to do that. Now notice I'm differentiating d squared, I'm not differentiating d, because well, the minimum point of d squared and the minimum point of the square root of that, which is d, is the same point, but it's easier to differentiate d squared than it is to differentiate d. And then you can see you get 0.05 hours, and that is a 20th of an hour. So in other words, 3 minutes. So 3 minutes after noon, the boats will be at their closest point. Now there's an alternative way to do this problem, and that means looking at the problem from the point of view of boat Q and using the information we're given in the first part of the question. Now previously what we did is we looked at the position of both boats with respect to the origin, and we proceeded from there. But now we're going to look at the motion of boat P with respect to boat Q. So boat Q is essentially our new origin, and we're looking at the motion of boat P as it moves along the 0, 1, 5 bearing. Now what we've done in the question is this. What I've done is this. I've drawn boat P at 3 different positions along the 0, 1, 5 bearing. The red vector indicates the position of P with respect to Q at the very beginning, and that's just 12 kilometres. Then I've drawn the boat at 2 other positions, a wee bit further on for the blue vector, and a wee bit further on again for the red vector. And we can clearly see it's when the boat reaches the blue vector. It's when the blue vector indicates the position of closest approach. You can see that clearly from the diagram. But look very, very closely again. The blue vector is making a right angle with the velocity vector, the relative velocity vector. So our question is this then. How long does it take boat P to reach the point where its velocity vector makes a right angle with its position vector? How long does that take? Simple problem trigonometry. Time is equal to distance divided by speed, and the distance is 12 sin 5. The velocity the speed we're told is 20 kilometers per hour. That gets our answer. Alternatively, we can use the scalar product, because the velocity vector and the position vectors are at right angles to each other, which means their scalar product is equal to 0. So in other words, if we dot the position of P with respect to Q with the velocity of P with respect to Q, the answer is 0. And since P with respect to Q is a function of time, we'll get an expression for T, and we should get the same answer in all cases. And that's how you proceed. That is an alternative way to proceed that gives you a wee bit more of an insight into problems of this nature and how we can use relative velocity vectors. Well, I hope you enjoyed that video, and I hope you found it useful, and if you did, you can pass it on to others and also give it a like. If you've got suggestions for other videos, or if you have any questions, just ask and I'll see what I can do. My name is Bernard Rosenberg. Thanks for watching The Young Scottish Physicist.